Morning. I'm Cameron Harr, obviously, at Lawrence Livermore, and I've been working over the past year on implementing a profiling tool developed at Oak Ridge with help from SARP and Fei Wing there. Fei is the developer. And calling it a high-performance profiler in the fact that it can get me results from a huge petascale file system pretty quickly. Now you'll see here has a title, Lustre Operations Lead. That's accurate, but it's only part of the picture. I only am allowed to allocate about 40% of my time to Lustre. So I am pleased with the stability of Lustre, that I can kind of get everything I need to done in that 40% of my time, but it also makes it hard to sometimes experiment and get some of that extra advanced knowledge that I want. Because of that, I'm not up to par with my predecessor, Mark Stearman, who many of you know. So Mark knew Lustre, knows Lustre still, I think, pretty well. And I got a subset of that knowledge, a small subset. I'm still working on it. I'm trying out the beard. That's a pretty recent addition. I'm not convinced it works, though. From my experience, the beard's good at catching and holding on to some things, but Lustre knowledge isn't one of them. So what am I talking about today? So we all have large file systems here, right? And they're growing. They're growing kind of on an exponential scale. And of course, with that capacity, we've got loads, heaps of data that's growing. And with that growth comes the growth in time it takes to understand what's on your file system. Case in point, if you do a DU or a find from the root of a petascale file system, it's going to take days, maybe a week or more to finish. And trying to do lots of such, I guess, using such tools on a regular basis, you're going to spend a lot of time not doing anything. So I think the community's been lacking a tool that can quickly get a lot of these file system characterizations that we might be interested in. For instance, do you know how many files and directories are on your file system? Do you know the sizes of the files and directories and their distribution? And what about Lustre striping? Are you familiar with how your users are striping their files? So these are some of the characterizations we've been interested in, and given that we didn't really have a good tool to cover those, that's why Dr. Wang went and developed Fprof. So most of you are familiar with Lawrence Livermore and Oak Ridge National Labs. They've had a presence at LUG for almost ever, I guess. And I don't know how many of you, though, know actually what we do. So I was going to give a brief site overviews. So Lawrence Livermore, where I work, they're primarily, funded and administered by the National Nuclear Security Administration, or NNSA. And our primary mission there is the stockpile stewardship. This is with Sandia and Los Alamos as well. Is we kind of maintain and help ensure the validity and effectiveness and security of the nation's nuclear weapon stockpile, as well as we're in a long multi-year project of modernizing those warheads. So overall, the lab has a basis in security, and besides the stockpile stewardship, we have a lot of just broad science, applied science and research all over the map, both in security topics and in just general science, biology, et cetera. Oak Ridge, also a US DOE lab, but they're all run by the Office of Science, like Argonne is that we just saw. And so because of that, they're much more open. They have a broader user base, I think a broader range of projects and programs that they work on, and they just do a tremendous amount of world-class research and science. Now, each of our two labs, we have kind of centers for maintaining the HPC resources. Livermore, we have Livermore Computing, LC, and we've got lots of flops and lots of bytes there. We have 4 main data center buildings, some with offices, some not. And our flagship facility, the TSF, or Terascale Simulation Facility, currently is pushing about 45 megawatts to the data center floor, and by 2022, when we get the Coral 2 system, it'll be up to 85 megawatts, and that's a lot of power. Part of the reason is we currently have 2 petascale systems on the same floor right now. We have Sequoia, which used to be number 1, now number 6, and we've now landed Sierra, which is our part of the Coral contract. Coral is a big procurement, stands for the collaboration between Oak Ridge, Argonne, and Livermore. And so our allocation of that is Sierra. It's projected to reach about 125 petaflops, and comes with a big GPFS install. Oak Ridge, so I'll go into LC's Lustre. So we currently have about 12 production file systems. 2 weeks ago, that was 13. As you can kind of see from this top graph, there's a lot of flux this year. We're adding file systems, we're retiring file systems. In fact, we're currently split right now between Lustre 2.5 and Lustre 2.8, kind of an old generation and a new generation. We tend to do a contract with a vendor for several years, and we'll exclusively obtain our Lustre systems from that vendor, and then do another bid process. So the previous vendor was a mix of Cray and NetApp, using the NetApp E-series with intelligent disk controllers. And that's on those systems we're running Lustre 2.5, obviously. In 2016, we had an RFP process that RAID Inc. won, and now we're using a collection of JBODs and servers provided by RAID. And both of these solutions, they have pros and cons. They're different. It's been a good exercise in going from an intelligent disk controller to a JBOD, and needing to use the intelligence of ZFS and other tools to get that management taken care of. But both solutions, or both vendors, I should say, have provided excellent technical support that we've been really happy with. This bottom table here, that actually comes from Splunk. We try to use Splunk effectively. We have a number of homegrown scripts and things that we dump files statistics to. You can see here, these are our unclassified file systems. I'll scratch H in the middle there. That's actually, I got another update today. It's about a little over 3.4 billion files right now in that file system. So a lot of files, but we're still able to profile it in a reasonable amount of time with Fprof. Okay, now Oak Ridge. So Oak Ridge has the OLCF, kind of like Argonne's ALCF. It's a little bit different. It's not an exact parallel of LC, but LCF is world-class computing organization, and the only drawback is, well, for Livermore, is they've got a more powerful senator, I think, and so they've got bigger systems than we do. So their flagship is Titan. Titan's at number 5. Beats out our number 6, and Summit is significantly larger than Sierra. So if any of you want to run for senator in California, please do. But we have similarities, we have differences. Oak Ridge uses LDiskFS, where we use ZFS as the back end, and Oak Ridge has 2 kind of twin 14 petabyte that's usable file systems that they cross-mount across the whole center, and have, as it shows, about 20,000 plus clients that access that. So we've also, at Livermore, started cross-mounting again. We did it for a while, went away from it due to stability issues, but I think Lustre's been stable enough that over the last year we've been re-implementing that center-wide cross-mounting. Okay, so Fprof, what is Fprof? As I mentioned, I think that we've been lacking a good comprehensive tool that can give us the file system characteristics that we've been wanting. And so Fprof is a Python-based, MPI-enabled tool that can go and walk the file system relatively quickly and provide all sorts of interesting statistics. We've been able to use it to preemptively address problems before it became a real problem, I guess. It's not a policy engine. There are policy engines out there, Robinhood, Starfish, that do a good job of what they do, but I think they have a different scope than what I want to do here. They're not maybe a true profiler that will give you a kind of an on-demand snapshot of what your data looks like. And Fprof is POSIX compatible. You can run it on different file systems. It has a lot of options, though, and some of those options are going to be specific to the file system you run on. For example, you can do a Lustre striping analysis. You probably won't want to run that on a GPFS file system. It's part of the pCircle project up on GitHub. On the inside, Fprof tries to use some efficient algorithms. So for workload scheduling, it uses a work stealing algorithm where processes that have finished their workload can go out and randomly ask their neighbors or other peers for additional work. And so if you've got maybe a particularly slow process that has a long work logs, then they can split off a chunk of that and pass it on to the asking process. That way it's kind of self-balances. You're not stuck with one slow process that hangs everybody up. On completion, it uses the Dijkstra-Scholten algorithm, which basically lets you dynamically add and remove nodes. Well, they'll add and remove themselves when they are assigned or when they complete their tasks. And then the root node, when it has no more children left in the tree and it's finished with its tasks, it can signal completion. And it doesn't have to worry about communicating with all of its peers and negotiating completion. We can also catch error codes without aborting. We'll get timeouts on files. Maybe they're in use or something, so we can't access them sufficiently to get their metadata information. So we can easily time out on those and progress. So if you want to try it out, it's up on GitHub. There's a couple of different ways you can grab it. We're using a Red Hat Enterprise Linux derivative, and so we don't always have the latest snazzy user space tools. So I just usually use the bottom version here. I just do a git clone and build it. I use the prefix option because I need to build one for RHEL 6 and for RHEL 7, since we have both types of clients. As I mentioned, Fprof has a lot of options. By default, these are some of the attributes or metrics that you're going to see in the epilogue. I've highlighted here some interesting numbers, maybe. So this is from a profile back in January. You'll see the file count back then was about 2.5 billion. Now it's up to 3.4 billion. You'll see the sparse files, about 1.7 billion sparse files. That's a lot of sparse files. We thought it was, at least, and so we asked why. Why is that? What's going on? I went around and talked to the number of application developers and maintainers and asked them. They had no explanation. It was a surprise to them as well. And it finally dawned on somebody that, oh, we're using ZFS with compression enabled, so a lot of these files are getting compressed, therefore their block count is lower than the file size would suggest, and we're using a simple algorithm to detect sparseness, and it was that ZFS compression that was falsely flagging these as sparse. Another number, 165 million files in a single directory. I don't think that's recommended. And so once we saw that, we immediately went and found out, well, I went and had Fprof add a directory size histogram so we could identify better where were these directories, these egregious directories, and then we were able to go to the user and work with them. And I think in this case, the user had every process printing out a new file for every time step, and it made a lot of files. Don't do that. If you want to run Fprof, you can run it with or without MPI. And there's a lot of options. The options aren't in the man page right now. That's on my to-do list. But again, you can run the help command and see some of those options. I'm going to run through and kind of show output from a sample run I did on one of our file systems. So you can see it here on the command line at top. So I'm running on 96 processes, and I'm telling it to set up a directory size histogram and to print out the top, the largest directories and the largest files. And then Fprof will print out kind of a prologue, tell you what it's going to do, and then it'll start going through and print out periodic kind of status updates that it's, what it's doing and its processing rate. By default, at the beginning, Fprof, while it's still kind of loading and getting up to speed, the scanning will be a little slow, and that will increase as time goes on. You can see here near the end of the profile that we're up near 60,000 files per second, which is about 20 times what it was at the beginning. So that's expected behavior. The epilogue is kind of where we get to see some of the more exciting stuff exciting for us type of weird people, that is. But you can see here that I was able to walk a billion file system about in less than 8.5 hours, which I think is pretty commendable. And again, we saw a huge number of sparse files, but now we know why. Again, these are mostly default metrics here. Moving on, you'll see this file set histogram. This is based on the file sizes. Again, this is also default behavior. Now this file system, LScratch RZA, it's a fairly new file system, and has a little bit different profile from some of our others. If you were to add up in your mind here, looking at the percent files, the fourth column there, we've got about 50% of the files that are 1 meg or less, whereas our other file systems tend to have a much greater number, like 80% or so, that are 1 meg or less. But this can help you understand, what your file size distribution is like. At the end, I've got that directory histogram. One thing I wanted to do was to look at empty directories. You can see 4.3 million empty directories. That might be a lot. Again, we asked why is that, and we think it's because of our purge policies. Oak Ridge and Livermore both have relatively similar purge policies. They differ in a lot of ways, but they're similar in they delete the files but not the directories, and so you're ended up with a lot of empty directories. You can see the five top files and directories as well here, and I've kind of obfuscated the names on those. Some other interesting finds. So these are two charts from a paper that Faye presented at SC in November. And the one on the left is one of our file systems, LScratch E. You can see we have a lot of small files. I think 88% of the files are less than or equal to a meg, but a lot of the usage of the file system, but 42% in this case, are from larger files greater than a gig. At OLCF, on their Atlas file systems, it's even more disparate. They've got 90% of their files are less than or equal to a meg, and 85% of their capacity is taken up with these larger file systems. And this is something that interests me in the fact that as I've kind of grown up in HPC, it was always drilled into me, HPC equals large, streaming I/O, big files. But I don't know if that's really the case. We can see proof here, that we have a lot of small files actually, and I have that open question in my mind of, what does the community in whole, what kind of file statistics do they see? Do they mostly have small files, or do they have that legendary large streaming I/O file set? As part of this paper, Oak Ridge also did a Lustre striping analysis through Fprof. And that gave us some interesting information. It showed us about 97% of large files. The striping analysis takes a threshold. The default is 4 gigs, so it only looks at files that meet, or exceed that threshold. So 97% of those files the Atlas file systems use the default stripe count. It's not completely surprising, but I think we would have hoped for a little bit more customization on the user's part. So here's a more in-depth look at that analysis. So again, about 97% use the default count of 4. In LC, our default count is 1, and Oak Ridge uses 4. The profile did find 21 different stripe counts used, customizations. But interestingly, there is no correlation between the file size and the stripe count. In other words, it's not like we saw striping used well with really large files. That wasn't the case at all. There's no correlation. And we saw some, where people actually decreased the stripe count to 1, and we are thinking those were kind of a file per process type job where striping is discouraged. So I think this is a great case, though, for PFL. Fortunately, that exists now. So as far as what Fprof takes system-wise, I guess I profiled the profiler to see what what impact it was having. My goals for running Fprof was to be able to run it monthly and not make much of an impact on the file system load or on taking up a bunch of batch nodes. We're running this through a batch scheduler, and I think Fprof has done well in all those cases. So I looked at the MDS load on a Lustre 2.5 system that used a single MDS node, because our 2.8 systems use D&E. And in general, I think it did pretty well. There's an orange line in the middle that's pretty flat. That was the mem usage. There was basically no movement. So we're not killing memory on the MDS node. Rather, the clients are the ones that have the workout with their memory. There's a moderate CPU hit. That pink jagged line kind of at the top, that's the % idle CPU. So you can see it's pretty idle. Fprof kicks in right there on the left side, immediately drops. But then it goes up to a moderate level of idleness, where for the most part we're not even 50% load on the MDS node. That shaded blue background, that's the system load. You can see that it has occasional peaks, and those peaks match up with the I/O weights, which is the dark blue. So there are the peaks, but overall, I decided this is a fairly moderate, but not overwhelming load on the metadata server, and we use LTOP LMS for monitoring and watching the IOPS there. We weren't peaking out on the IOPS as well. So I don't think the metadata node is a bottleneck here. As far as problems we ran into, we hit some. We found a couple, like small bugs here and there that Fabe fixed pretty quickly. The bigger issues came from other things. One of the more time-consuming one is more of a policy thing. We disallow users to submit root jobs, and you need root or super user access to walk everybody's files, right? And so it took a while to get this approved and implemented. I was using sudo at first, and it worked, and then it stopped working, and I had to implement another workaround, but it's running now. Another problem was crashing jobs. So we were defaulting to an unlimited Lustre lock usage model. We weren't restricting that, and it didn't cause us problems until we tried running Fprof. We'd get OOMs partway through the job, and if you can imagine on multi-billion file systems, you're going to have a lot of locks as you walk that, and so all you have to do is limit that somewhat. You can be fairly generous, like 12,000 here, and that will help avoid the crashes. We have Rel 6 and Rel 7 derivatives on clients and servers, and so had to build two different versions of Fprof, but again, not a big deal. One outstanding issue we're still running into is one of our client clusters. It's relatively new. It seems to move pretty slowly, and we don't know why. There seems to be a bit of a correlation between when we applied some Spectre meltdown patches in the February timeframe and when I noticed the slowdown. Correlation's not causation though, so we're not sure if that's it or just a coincidence. Going forward, some things we want to work on, we want to, as I mentioned, better detect sparse files. May need to search for holes in the file, although I think there's limited Lustre compatibility with that. Something we need to look more into. We want to make sure that Fprof works with Python 3. I think RHEL 8 will only have Python 3, not Python 2. So we need to make sure that gets working. We need to update some of the documentation, man pages. And one thing I'm really interested in is having the community, try it out and provide input. Add features or find ways we can improve this. Or as I mentioned earlier, kind of understand community-wide, what is a typical HPC workload, if there even is a typical one. And that's it. Thank you. Any questions?